Hi, Corey. I thought it was just going to be me for a while.
No, I'm here. Good morning.
I was going to get all sad. Has anybody ever told you you're in a class by yourself?
No, never.
I just did.
I'm sure others will join.
All right, it's 8 o'clock. We'll get started. It's just you and me, kid.
All right.
All right, so we're looking at predicting the sign of delta G naught. And what we can see here is that there's this little table here that's based upon the equation that we talked about the other day, which is the delta G equals delta H minus T delta S. And what we can do is if we know the signs of delta H and delta S, then we can have a go at least at predicting the sign of what delta G is going to be. Now, the background we need here is that if delta G is negative, the reaction is going to be spontaneous. And if delta G is positive, then the reaction is going to be non-spontaneous. Now, what do I mean by spontaneous? Spontaneous means that it's going to go pretty much of its own accord. And non-spontaneous means it won't go of its own accord. That's really it. You can have spontaneous slow, spontaneous fast, but spontaneous is still spontaneous. So what we can talk about here is this relationship between the signs of delta H and delta S and how that plays into the sign of delta G. Okay. This is not a diagram you have to memorize. It really is based on common sense and a little bit of math. So what we've got are positive values of delta S up here, and negative values of delta S down here. Positive values of delta H on what's the x-axis, and negative values of delta H on the other side of the x-axis. Let's first of all talk about the situation where delta G is negative and we're always going to be dealing with spontaneous processes. So in that instance, here's how it works. If you've got delta H is negative and you've got delta S is positive, and then when we put them into our delta G equation, you can see what effect that's going to have. So we have a negative value here for the delta H minus T. Now remember T is Kelvin, so it's always going to be positive, times a positive value. So what I want you to see here is that you've got a negative value minus a positive value, which is always negative. This is what I mean about not having to memorize this. So in this quadrant here, when we're dealing with negative delta H and positive delta S, then we're always dealing with a spontaneous process. Okay, does anybody here have any questions? Okay, so delta G is a negative, spontaneous always. Now, why does this make sense? It makes sense because if we're dealing with a negative delta H, that means that it's going to be an exothermic process. And exothermic means it's releasing energy. That makes it more favorable. The other thing is that we're increasing entropy or increasing randomness. And we talked about entropy the other day. So we're increasing entropy, and you know that any process that increases entropy is going from the reactants to the products is going to be a favorable one as well. So it makes sense that processes that are always spontaneous are always going to be ones that are exothermic, they have a negative delta H, and will increase their entropy. So that's going to give a positive delta S. All right, any questions? Any questions so far? Okay, let's take a look at the other extreme case that we can talk about. And that is when we have a positive delta H, that's an endothermic process, and a negative delta S, that's a process where entropy is going away or going down. So let's see what happens here. I think you'll be pretty clear about what's going to happen in this case. We've got a positive value, and then we're subtracting T times a negative value. So what you can see here is it's positive minus a negative, and T is always positive. So this is always going to be a negative value, and we're subtracting a negative value. That means we're adding. So that means we're going to get positive all the time. So in this instance, these are always going to be non-spontaneous processes, which I think makes sense because endothermic reactions are kind of the worst reactions because energy has to be taken in. And then the delta S, and this is going from the reactants to the products, of course, and delta S is going down. So the entropy is decreasing, and that's not good either. So a combination of two things that aren't good is going to lead to this non-spontaneous process. So delta G down here is always going to be positive, and that means it's going to be non-spontaneous all the time. Okay, does anybody have any questions so far? So let's look at the other two combinations. You'll notice that the ones we've dealt with so far are the ones where we've got a different sign for delta S and delta H. One's positive and one's negative. In those instances, it's either going to be spontaneous all the time or non-spontaneous all the time. The cases we're going to look at now, though, are cases where the signs are exactly the same. So let's look at a situation now where we've got delta H is going to be a positive value and delta S is also positive. So the enthalpy is not favorable, but the entropy is favorable. So what happens here in this case? So let's take a look at the equation again. Delta G equals delta H minus T delta S. Now this one's not as clear as the other ones. So we have a positive value minus T times a positive value. So in this case, the sign of delta G is going to be entirely dependent on this temperature here and what the value of that is. So what I can say is that at low temperature, and if you wanted to, you could just say, well, what would a low temperature be? Let's say 0, even though you could never have 0 because it'd be Kelvin, but let's say it was 0. You could certainly see that if T was 0, that this whole thing here would be 0. So it'd be positive value minus 0. So you know that what you'd get would be a positive value. So at low temperature, we're going to, delta G is going to be positive, and it will be non-spontaneous. And at high temperature, this one's a little bit harder to see, but if at high temperature, I want you to imagine that there'd be a value of T that you could put in here where it would be, this T times a positive value would be greater than the positive value that we have for the delta H, which would mean that it's going to be negative. So delta G would be negative at high temperature. And that means it would be spontaneous. So you can see that when delta H is positive and delta S is positive, then the sign of delta G is going to depend on the temperature. It could either be positive or negative at low temperature or high temperature respectively. And that tells us that it's going to be non-spontaneous or spontaneous depending on the temperature. Does anybody have any questions? Okay. So I'm hoping you're beginning to see that you don't have to memorize this chart. You can just plug in the values like I've been doing here, and that will give you a pretty good idea of what's going to go on. Okay. The next one, delta H, is the last one. Delta H is negative and delta S is negative. So in this case, delta H is favorable, but the delta S is not favorable. Again, we're going to get this variation with temperature that we had earlier. But it's going to be the opposite way around. So we're going to have a negative value minus T times a negative value. Now this one is a little tougher to see, but if you have a low temperature, then delta G is going to be negative, and that's going to be spontaneous. And at high temperature, delta G will be positive, which would be non-spontaneous. So again, talking about low temperature, just choose a low temperature like 0, and you can see that delta G would definitely be negative, which would make it spontaneous. But then you can also imagine a case where temperature was large enough so that negative minus a negative value, which is really adding, would overtake the negative value. We'd end up with a positive value for delta G, which would lead to a non-spontaneous process. So in summary, here's what I can tell you. When the signs are different, when delta H and delta S have different signs, then it's going to be spontaneous always or non-spontaneous always. When they have the same sign, then the spontaneity is going to depend on the temperature. It'll be spontaneous at a high or low temperature and non-spontaneous at low or high temperature. All right, does anybody have any questions about this? That's pretty much the background for that. It's really not too bad. So here's an example. So here's a reaction I want you to consider. Now, I give you the actual reaction. Of course, I give it to you balanced. And I also tell you over here whether it's endothermic or exothermic. Now, what we had talked about previously about enthalpy was that if delta H is negative, then we're talking about an exothermic process. If delta H is positive, then that's an endothermic process. So from that, we're always going to know exactly what the sign of delta H is automatically, because I'm always going to tell you whether it's endothermic or exothermic. Further, what I can say is the entropy really has no effect on the delta H. So whether delta S is positive or negative is not going to tell you whether delta H is positive or negative. The only thing that tells you if delta H is positive or negative is what I've got written over here next to the reaction. It's either going to be endothermic or exothermic, in which case, you apply the sign that I listed up here. So that's the easy part. Now we need to predict the sign of delta S. Now I gave you a bunch of rules earlier about entropy, and I'm going to return to those up here. And the one I'm really referring to here is entropy of gas is greater than ions, is greater than liquids, is greater than solids. So I went through all this the other day. But the point is that the gas is going to be greater than aqueous liquids and pure liquids than solids. So looking over here, you can see that we have stuff in the gas phase and we have stuff in the solid phase as well. What we can do is we can count up the molecules on each side that are in the gas phase. That's really going to be the only thing that's of any importance here for entropy. So on the reactant side, you can see that we've got 8 molecules, so 8 gas, going to 12 gas. And the solid here is not going to be important at all because the solid is not really going to contribute very much to the entropy. We're only interested in what's happening with the gas. Now, just on a pure intuitive basis, what I'd like you to appreciate is that there's more ways to arrange 12 gas molecules than there are 8 gas molecules. Now, delta S is always going to be the sum of the entropies of the products minus the sum of the entropies of the reactants every single time. That's going to be our standard equation for entropy. And you can see here that if we did just a simple math here and said 12 minus 8, then we'd end up with positive 4. So what that tells us is that there's more entropy on the product side than there is the reactant side. And that's really all I want you to get here. So more entropy on product side. Okay, I'm going to stop here for a second. Does anyone have any questions about this? There's a real danger to overthinking this. And I want you to think of it in the simplest terms possible. When I tell you that there's more particles and that means there's more entropy, I just want you to go with that. So if you're going from a situation where there's fewer molecules to more molecules, I just want you to appreciate that entropy is increasing. That's it. That's all I want you to think about. So in this instance, we know that delta S is going to be a positive value. Now, from the information I've told you up here, it does say it's endothermic. That means that delta H is going to be positive as well. So after that, you can then apply your equation just like we did earlier. And we'd have a positive value minus T times a positive value. And we can tell from this that it would be at low temperature, it'd be non-spontaneous. And at high temperature, it would be spontaneous. And that's it. Low temperature, I'll just put in here negative delta G, just to clarify that, and positive delta G for the high temperature one. All right, does anybody have any questions about this? About either part of that problem? Okay. I will show you what the test questions look like in a minute. Don't panic about that. But let's look at one other example here. And this one involves a solid on the reactant side and then aqueous ions on the product side. And this one says it's exothermic. Remember, you'll always be told whether it's exothermic or endothermic. So the first part of this is to predict the sign of delta S. And the situation we have here is that we've got a solid going to aqueous ions. Now, as I showed you earlier, entropy beats ions in entropy of gas beats ions in solution, beats liquids, beats solids. So solids are at the bottom. So the aqueous ions are going to be what's telling the story here. And for this one, we have 0 aqueous ions on the reactant side. So AQ ions, 0 AQ ions is going to, let's see how many, 2 plus 1 is 3. So 3 aqueous ions on the product side. So what I want you to be able to do with that immediately, I'm hoping you can look at it and say, oh gosh, entropy is increasing. So I know that delta S is going to be a positive value. Okay, so anybody here have any issue with looking at that and saying entropy is increasing? I mean, just again, don't overthink it, just look at it. If the products are less than the reactants, the entropy is decreasing. That would mean delta S was negative. Right, so if this was, say, 6 ions going to 3, or 10 ions going to 3, I'd want you to immediately know that delta S was negative because entropy was decreasing. Now, from what we have up here, we can see that delta H is exothermic. It says exothermic, so delta H is going to be a negative value. Whoops, negative. So we plug that into our equation. And you can see we have a negative value minus T times a negative value. T times a positive value, which would be always negative, which would mean it was always spontaneous. All right, does anybody have any questions? Okay, so I said this earlier and I'll say it again here. When the signs of delta S and delta H are the same, then there's going to be variation with temperature. But when delta S and delta H have different signs like they do here, then there is going to be no variation with temperature. It's either going to be spontaneous or non-spontaneous under all conditions of temperature. All right, does anybody have any questions? So I've laid out pretty much laid out all the background here. Let's take a look at, what I'm going to do is I'm going to open up what an old test would look like. And then I'll show you how that applies to the test that you'll be taking as well. I think it's going to be more useful for you to see that. Let's see. I'll open up a key here. It might be easier. All right, so look at the question you have here. This will be similar to what you'll see on the test you'll be taking as well. So we've got, let me enlarge that a little bit. There we go. So we've got 2Cu3PO4, but notice the state on it says solid. Then we've got 3H2SO4 aqueous, 3Cu2SO4 aqueous, and H3PO4 aqueous. And notice I say here that it's exothermic, just like I did in the other problem. So the idea here is, again, to count these aqueous ions. Now, I know you're looking at this and you can't really see the ions. So what you should do here is draw a picture of what those ions would look like. So we'll have 2Cu3PO4, and that's a solid. And then we'll have 3 H2SO4s. And if I draw a picture of H2SO4, it looks like this. So 2 H's and the SO4. How do I know to split it up? I know to split it up because it has AQ next to it. Anything aqueous means it's dissolved in water, dissolved in an aqueous solution. Anything solid means it's coming out as a solid. If I count up the ions here, it's 3 times 3, which equals 9 aqueous ions. I'll stop here for a second. Is anybody having any questions about counting up 9 aqueous ions for that? Okay. Over here, we've got 3 Cu2SO4s. Now the Cu2SO4, maybe 2 Cus and, and 1 SO4. You really don't need the charges, but I'm putting them on anyway. That would be 9 aqueous ions as well. And then we've got 2 H3PO4s. And that would look like 3 H's and a PO4. So we're using a lot of the same techniques as we talked about for test 2 in splitting up equations. We really did hit that pretty hard during test 2, I think. And that would be 8 aqueous ions over there. So if we were to add up everything on the reactant side and the product side, and remember, we're only interested in the aqueous ions because they're the ones that are going to contribute mostly to the entropy. The situation would be 9 goes to 17. So 9 AQ goes to 17 AQ. So from there, I'd want you to see that delta S is going to be a positive value. Does anybody have any questions? Now, once we've determined that delta S is a positive value, then we can apply what we're seeing in the rest of the problem. So delta S is positive. delta H is negative. So it's the same situation as we had earlier. And you can see that it's going to be spontaneous at high temperature and low temperature. All right, does anybody have any questions about that question that we just went through? Well, let's take a look at how this relates to what you'll be doing on the actual test here. All right, here we go. Now remember, I do have videos for all of these problems, and especially for this one, because it's kind of a word problem and sometimes people don't really understand what I'm looking for with it, but just read it carefully with me and we'll go through it. For the reaction below, determine the difference in relevant particles to allow for the determination of the sign of delta S. I know that sounds really complicated, but all I'm really asking you to do is look at it and say, well, what's the relevant particle here? The relevant particles here are the ions, the aqueous ions. The solid is not relevant at all. So we're only interested in the number of aqueous ions. What I'd like you to do, give this a go now, see if you can figure out the total number of ions on each side of the equation, please, and then what the sign of delta S would be. I'll give you a minute or two for that. All right, let's see where we end up with that. So what I'm seeing for the 2LiClO3, I'm seeing, oh, that's an interesting one, isn't it? So let's break that up. We've got 2, and it would be Li, and 1 ClO3. Now, often in this situation, people will say there's 3 ClO3s. There isn't, just the 1. So the total there is 4. That's 4 aqueous ions, just for that part. Then we've got the Li2S, and there's only one of those. And that's going to be 3 aqueous ions right there. I'm going to stop here for a second. Does anybody have any questions about the ions here? All right, let me ask you all this. I told you that we know there's only 1 ClO3. How would you know there were more if there was more than 1? Any idea?
It would be in a parentheses and then there would be a subscript.
That's right. It'd be like this. It'd be PbClO3 and then be 4. Now that would tell you that there were 4 of these particles, or 4 ClO3s here present in that diagram. That's something that sometimes people run afoul of. And let's see, what have we got here? That's interesting. Doesn't seem to be quite balanced properly, does it? Got the same thing over here. That should be CuClO3 over there. All right, I'll have to fix that. Doesn't really change anything, but I'll go ahead and fix that. So it'd be 2 CuClO3 and that would be 4 aqueous ions. And the solid we just ignore. We don't worry about that. So it would be 7 aqueous goes to 4 aqueous. And look what the question's asking for though. It says the difference in relevant particles. Now, delta S is always products minus reactants. So in this instance, the difference would be 7 minus 4, which is -3, which is the answer I'm looking for there. Sorry, 4 minus 7. Sorry about that. 4 minus 7, which is -3. Now, on an intuitive basis, you can see that we're decreasing entropy. So that's how we're getting this negative value here. So it'd be 4 minus 7 is -3. Does anybody have any questions? I take a look at the answers here. You can see it's all multiple choice. And I would choose -3 as my answer.
I have a question.
Yeah, Georgiana.
Where did you get the 4 and the 7 again? Like where
Okay, so
the
4.
P minus R? Yeah.
4 and 3 is 7.
Okay.
And then 4 over here on the product side. So this is all the reactants, right?
Oh, reactants and products. Okay, got it.
There's all your reactants and there's products over here. Remember that the solid doesn't play into it. Is that okay?
Yeah, that makes more sense.
So when you know how to do that, it's actually not too difficult. But the main thing is just being able to break these apart properly and making sure you count them up correctly. And if you do that, then you won't have any real problem with number 5, I don't think, on the test. Now remember, if you do forget this, you can go look at the videos that goes through how to do all these problems, and that's how you could know how to do this as well. Now, question 6, this is where we apply that whole thing with it being exothermic and figuring out the sign of delta S. But I will share something with you here. In these kinds of problems, you're always going to be able to tell what the sign of delta S is simply by looking at where the solid is. And you can say that if you've got solid over here on the reactant side, you already know it's going to be much lower in entropy than the reactants, which is going to be 2 sets of aqueous ions. So just looking at it, you'll be able to tell, oh yeah, well, entropy is increasing because we've got solid going to much more aqueous ions. I wouldn't even have to count them. If I did want to count them, it would be 4 for the 2 NaCls, then it would be 3 for the Na2CO3, and 3 for the CaCl2. So it would be 4 going to 6 if I was doing that. So I know that delta S is positive. So for something like this, I can see that delta S is positive just by looking at it, and delta H is going to be exothermic. That's going to be negative. And then I can apply what we talked about earlier to determine which situation applies, whether it's going to be spontaneous at all temperatures, non-spontaneous, or whether there's going to be variation with temperature, as we talked about earlier. And that's all there is to it. Does anybody have any questions about either question 5 or question 6 on the test you'll be taking? Come on, that's easy points, folks. That's easy, easy points. You shouldn't have any real difficulty with that at all. Don't forget there's also the fun quizzes, the extra credit quizzes. They're a little bit different, but that you shouldn't have too much trouble with those either. All right. Let's go back to where we were at here. Okay. So we've already talked about the free energy calculations. Did that the other day. I'm going to just do a somewhat short introduction into electrochemical cells and what we're dealing with there. Enlarge this a bit. Okay, remember you have access to these diagrams, in color actually, as far as the PowerPoint goes. These are a printable version of the same thing. Not quite as clear, but you can see what I'm getting at here in this diagram. So this is the science behind batteries. The batteries that run, pretty much all of your electronic devices that run on batteries. So this is how they work. So in this situation here, we've got zinc and then we've got copper. Now, what I would want you to see here is a couple of things. First of all, if you look at this zinc, it's dissolved, well, it's not dissolved, it's sitting in a solution of zinc ions. And over here, we've got copper metal, which is sitting in a solution of copper ions. Now, I'm going to change this share here, hang on. Share the sound. And I need to make sure that you all understand the difference here between aqueous ions and solids and how to tell what they are. I know that might sound easy, but sometimes people get mixed up with it. Let's see, introduction to electrochemical cells. I'm not going to play the whole thing.
Galvanic cells. These are electrochemical, and what that's doing in the middle.
I also call them galvanic cells.
And it has a charge of 0. So when zinc has a charge.
Okay. So when we're looking at zinc and comparing it to what zinc 2+ is and copper 2+ and what copper is, we know that zinc solid is this solid metal. It's a solid silvery metal. Zinc 2+ is ions in solution. And you can tell, I mean, it's in a flask, it's in a solution. You can't see anything dissolved there because it's all dissolved in the water. And then you've got copper 2+, which is this blue aqueous liquid. And then you've got copper solid, which is this solid bar. All right, does anybody have any questions about what I mean by the difference between ions in solution and solids? Okay. I know that you'd be surprised sometimes.
0, it just looks like this, and it's turning into zinc 2+, and you can see the difference here. The zinc 2+ is an aqueous solution. And what's happening is the zinc is actually giving up 2 electrons when it's forming zinc 2+.
Hang on. I'm just trying to get rid of this.
Those particular 2 electrons, those very 2 electrons are going to be now taken up by the copper 2+ on the other side of the solution.
Okay. So going back to our diagram here, we've got our zinc solid, which is in a solution of zinc 2 plus, and then we've got copper solid, which is in a solution of copper 2 plus. Now, what's going on? Take a look at what's happening with the zinc. Do you see how it's got this jagged edge down the bottom here? That's indicating that the zinc is actually dissolving. It's actually going into the solution. Essentially, what's happening is that the zinc solid is turning into zinc 2 plus ions. So it's dissolving. That's an oxidation process. And if you think about oxidation as being rusting, you know that that's what happens when things rust. They waste away, they dissolve, right? So copper, on this side, you can see the opposite's happening. Now, it's a little bit subtle in this diagram. It's harder to see. It's easier to see it in the color diagram, but this is actually getting fatter. So copper is actually plating on the surface of the copper metal. So this is actually getting thicker over here with the copper. So copper 2 plus ions that are in solution are actually turning into copper metal. Now, how's that occurring? Well, it's occurring because electrons are being given up by the zinc and are going over here to the copper side, and it's these electrons that do the work. So in a battery, it's that flow of electrons that powers whatever we're powering. Now, how effective this is, or how many electrons we get, or how much voltage we get, is going to be determined by the difference in voltage in these two systems, which we'll get to in a little bit. The solutions here are called electrolytes. They conduct electricity. Now, you'll also notice something else here called the salt bridge. If we don't have this salt bridge, it won't work at all. Now, the idea behind the salt bridge is that if you take a look at what's happening with the zinc, I said that the zinc is turning into zinc 2 plus, and the copper 2 plus is turning into copper. What that means is on the side of the copper, there's less positive ions, and on the side of the zinc, there's going to be more positive ions. So what's going to happen is that negative ions, the counter ions, in this case, it's sulfates. The sulfate ions will actually flow through the salt bridge to the other side, from the copper to the zinc side. And this is to maintain electrical neutrality. Because if we didn't allow this, all we'd have would be electrons flowing through this wire, but no place for negative ions to go. So the negative ions then flow in the opposite direction to where the electrons are flowing. But they're always going to flow through the wire here, and then the ions will flow through the salt bridge. And that's to maintain the electrical neutrality of the system. Does anybody have any questions? So let's look at an introduction to some terms that we're going to be working with here. The first one is oxidation, and oxidation is loss of electrons, and reduction is gain of electrons. You can remember that by the mnemonic oil rig. Oxidation is loss, reduction is gain, oil rig. So the electrons being lost are the ones that are going through this wire here from the zinc side over to the copper side. So it's the zinc that's giving up the electrons, which means the zinc is undergoing oxidation, and you can see that it's wasting away. The copper is undergoing reduction. You can see that that's plating as well. So I say that that's dissolving on the zinc side. I say it's plating on the copper side. You might have heard of the process called electroplating. Well, this is it. This is what electroplating is. We have two terms that we use for the sides of the reaction. We have electrodes, which are the zinc metal and the copper metal. In a battery, that's the poles. You know, it's the top and bottom of your AA or AAA battery. They're the electrodes. That's what actually makes the contact with the device so that you can put the electrons through it. So those are the electrodes, and we have an anode and we have a cathode. Now, in the case of the anode is where oxidation occurs, and cathode, that's where reduction occurs. It's easy to remember which is which because oxidation and anode both start with vowels, and reduction and cathode both start with consonants. So it's easy to remember that anode is where oxidation occurs, cathode is where reduction occurs. In other words, rusting or dissolving occurs on the anode side, and plating always occurs on the reduction side. Now, when I say zinc is dissolving, what I mean is zinc solid is turning into zinc 2+. And on the other side, copper is building up or plating. Copper 2+ is turning into copper. Does anybody have any questions? So instead of drawing out these diagrams like this and showing, the pretty pictures and all, we have a shorthand way of presenting these electrochemical cells. And what we use is what's called a cell diagram. Now, by convention, the anode is always going to be first in the cell diagram. The order on each side of the cell diagram doesn't matter. The salt bridge, or what separates the cells, is always represented by these two vertical lines here. So we can tell on this side, this will be the anode and this will be the cathode over here. And again, the order on each side doesn't matter. You can have these in any order you like. It's not going to be important. So what we're interested in here in any electrochemical cell is what kind of voltage we're going to get from it. Does anybody know off the top of their head the voltage they're getting from a AA battery? Any thoughts? It's actually written on the battery. It's a 1.5 volts. And as we'll discuss later, a AA, a AAA, a C battery, D battery, they all actually are 1.5 volt batteries. They're all 1.5 volts. The reason for that is because all of them are using the same chemical process in order to generate electricity. All of them, exactly the same. The only difference between those batteries, of course, is their size. The smallest ones are the AAAs, then the AAs, then the Cs and Ds. And that has an effect, obviously, on how long they last in the device that you're dealing with. We'll talk a little bit more about that in a second. So let's say we have our cell diagram here, and we're interested in how much voltage we're going to get out of this zinc copper cell that we're talking about. Remember, it's the electrons here that are doing the work, and we can put a device in here to run using these electrons. We need to know what kind of voltage we're going to get from this system. So here's what we do. We use what's called a standard reduction potential table. Let's see if I got it here. No, I haven't. All right, let me go back to here. I thought I'd put this up, but I haven't. So in the test 3 folder, yes, we've got this tables here. We've got enthalpy, entropy. This will also tell us each cell as well. So we have these tables. Obviously, if I'm giving you a table, you don't have to memorize anything. Let's see if we can find those. I think, yeah, they're more towards the end here. So these are standard electrode reduction potentials. So these are the voltages for different processes that can occur on each side of an electrochemical cell. One thing you'll immediately notice is that it says reduction potentials. So we're dealing strictly with reductions here. Now, as I had told you earlier, oxidation is loss of electrons, reduction is gain. And what you'll notice about every last one of these reactions is that the electrons are on the reactant side. I'll say it again, the electrons are on the reactant side. What does that mean? It means the electrons are being gained. If the electrons were on the other side, that would indicate oxidation. So if electrons are being gained or accepted, that's reduction. Every last one of these is a reduction that we're talking about here. And you can know this because it actually even says it in the table. Standard electrode reduction potentials. So that every last one of these is a reduction that we're talking about. Now going back to the thing here. Let's wait for that to go away. This is the cell diagram that we're talking about. So on one side, we're dealing with zinc and zinc 2+, so zinc electrode in zinc 2+ solution. And on the other side, it's copper in a copper 2+ solution. So I have to do this again, it has to go away again. So I have to find reactions that have exactly those species in them so I can write them down. So let's see, where's the one with zinc and zinc 2+? There it is. So zinc 2+ plus 2 electrons gives zinc, and that's going to be negative 0.763 volts. So that's what I would write down. I also need to find the one that involves copper 2+ and copper. Now I've got to be a little bit careful here because there's one up here that involves, see, copper 2+ and copper+, but that's not the one we're talking about. This one here is copper+ and copper solid. That's not what we're talking about either. It's this one here that goes from copper 2+ to copper solid, and that has positive 0.340 volts. So what I'm doing over here is I'm writing down those reactions from the reduction potential table. I want you to understand that only ever one equation will ever match. I'll say that again. Only one equation will ever match. And it's going to always be easy to tell. Now, a couple of things you're not going to see in a cell diagram. You're not going to see electrons. You're not going to see water. And you could see H+, but you could also see H3O+. Those would mean the same thing, H+ and H3O+. So you should think about those as being equivalent. Because in the in the potential table you're looking at, it's possible it could be expressed as H+ or H3O+. So you've got to be a little bit careful about that. So as I said, you're only ever going to find one equation that matches the situation on each side of the cell diagram. So in this case, zinc 2+ plus 2 electrons gives zinc, and we found our E0 as that's the cell potential, or the half cell potential for that part of the cell diagram, as being negative 0.763 volts. And then we've got copper 2+ plus 2 electrons gives copper, and that's going to be positive 0.340 volts. Again, I just pulled them directly off the table. So these are the rules that we have for dealing with half cells. And these are called half cells because they're each one half of the cell. If I flip the reaction, I change the sign of the voltage. So if I was to flip this zinc reaction here, of course, it would be negative 0.763 as it is here, but if I flip it, it becomes positive 0.763. And this one's important because it's not very intuitive here, but if I multiply the reaction, I don't multiply the voltage. And that's because voltage is what we call an intrinsic property. All right, let me talk a little bit about intrinsic and extrinsic properties. An intrinsic property is a property by which it's something that doesn't depend on the amount you have. A property that doesn't depend on the amount you have. I'm going to give you some examples of these and you'll see it's not too difficult to figure it out. A good example of an intrinsic property is boiling point. See, if you have a kilogram of water or 10 kilograms of water, it's always going to boil at 100 degrees Celsius. So boiling point is an intrinsic property. Melting point, of course, is an intrinsic property as well. Another good one is density. If you've got 10 kilograms of water, it's going to be 1 gram per mil. 1 kilogram of water is still 1 gram per mil. So density is an intrinsic property too. Some other examples, color is a good intrinsic property. If I've got a kilogram of copper sulfate, it's blue. If I've got 10 kilograms of copper sulfate, it's still blue. So you're getting the idea now about what an intrinsic property is. Now, extrinsic properties are the opposite. Those do depend on how much you have. And those are fairly simplistic. Things like mass, things like volume, things like length, those are all extrinsic. You know, the mass of something always depends on how much you have of it. But this property we're talking about, voltage, is actually an intrinsic property. And if you want proof of that, think about what I was talking about earlier, batteries. AAA, AA, C, and D. Those are all batteries that use exactly the same chemical process. And yet they're all different sizes. They're all chemical processes that produce the same voltage, 1.5 volts. I remember back when I was young, back in the Stone Age, I had this device called a boombox. I don't know if you know what a boombox is. It's kind of like a cassette player. I don't know if you know what a cassette is. Anyways, it's the speaker system kind of set up, and it took D batteries. But if I was really desperate to listen to something, I could always put a AA battery instead of a D battery in instead, and it would still work. What would be the catch? Anybody know what the problem was with that? It wouldn't last.
AA wouldn't last as long?
And it doesn't last very long. Like, you can do it, but it's not really advisable. No, it doesn't last very long. There's not very much material to react in the AA cell, so you end up it ends up running out pretty quick. D batteries last a lot longer. But the point is, it's the same chemical process producing the same voltage, but they're clearly different size batteries. And that's because voltage is an intrinsic property. So how do we deal with that? Well, I've already stated here that in a cell diagram, the anode is listed first. And by extension, of course, if that's the anode, then the other thing must be the cathode. Now, I already told you back over here that anode is where oxidation occurs and the cathode is where reduction occurs. When I went to that table, it was a standard reduction potential table. I took off 2 reductions. They're both reductions here. I already stated here in the cell diagram that automatically the anode is listed first. So what I want you to realize from that is if these are both reductions, then the first one is going to have to turn into an oxidation. How do we do that? Well, it's fairly simple. We just flip the reaction. So if I turn this around and put zinc solid goes to zinc 2+ plus 2 electrons, that's going to turn that into an oxidation. But in so doing, I also have to flip the sign on the E0 as well and make it positive. So let's do that. So I flip the zinc equation because it's undergoing oxidation. And why do I do that? Because by convention, by definition, the oxidation, the anode, is always listed first. I'll say it again. By convention, the anode, the oxidation will always be listed first. Every single time. It's never going to change. I'll say it one more time. The anode is always listed first. So in a cell diagram, you can come up with a very simple rule. The first thing you see on the salt bridge, first thing before the salt bridge, you're always going to flip that equation. Every single time you're going to flip it based on what you see on the standard reduction potential table. So that's what I did. I flipped the zinc equation. It becomes zinc goes to zinc 2+ plus 2 electrons. And you can see the E0 now changes to positive 0.763 volts. All right, does anybody have any questions so far? You'll notice I did not change the copper reaction at all because it's a reduction and I want it to stay a reduction. Now what I can do is I can add these two reactions together. Remember, these are called half reactions. I can get the whole reaction. I also can get the voltage on the cell. And by adding these two voltages together, I get 1.103 volts. And per significant figure rules, I've got 3 places past the decimal, 3 places past the decimal, which gives me 3 places past the decimal. And this is called the cell potential. So that would be the cell voltage. It would be like the voltage I talk about with the AA and AAA batteries, 1.5 volts those, but this one is 1.103. Does anybody have any questions so far? Okay, we can also find from this delta G if we know what the cell potential is. And what we're using here is this equation, negative NF E0 cell. Now, N here is the number of electrons transferred in the balanced equation. In this instance, zinc is giving up 2 electrons and copper 2+ is gaining 2 electrons. The electrons transferred is simply 2. 2 from the zinc side over to the copper side. So whatever you're seeing here in the equation, that's going to be your N value. F is a constant. It's called the Faraday constant, and it has the value 96485 joules per volt per mole. You don't have to memorize that. I always give you that value. And if I wanted the delta G value here, I could see that it would be -2 times 96485 times 1.103 volts cell voltage. And then I can convert that into kilojoules, and I would end up with a delta G value here. You'll notice it's negative. That means that the process is spontaneous and always will be spontaneous as long as the E0 cell is a positive value. Does anybody have any questions? So this is just by way of introduction. I'll show you the problems that involve this stuff in a minute or a little while. So here's another example. Let's say we wanted to find E0 cell, delta G, and K for this cell. So we've got copper 2+ and copper on this side of on the left-hand side of the salt bridge. And then we've got H2SO3 aqueous, S solid, and H3O+. And I've also got this platinum over here as well. Now, if you look closely at this solution, you've got, or what's on this side, the right-hand side of the cell, we've got an aqueous solution with the H2SO3. We've also got solid sulfur, and then we've got H3O+. Now, solid sulfur is not a conductor. It's an insulator. It's a non-metal. So I can't use that as an electrode because it can't carry electrons. So in order to carry the electrons into this side of the solution, I'm going to have to use a platinum wire. I choose platinum because platinum is a fairly inert metal and it's not going to react with anything. But the bottom line here is that if ever you see platinum as part of the cell diagram, you simply ignore it because all it is a conduit for electrons. A lot of the time people see PT and they say, well, look, I can't find anything that's got H2SO3, sulfur, H3O+ and platinum. You'll never see the platinum. Platinum will never be part of the equations that we're talking about. So I've already showed you where the copper 2+ and the copper reaction is, and that's this one here, positive 0.340 volts. So I'd have to go hunt down now the one that had H2SO3. Let's see if I can find it here. H2SO3, there we go. It's right here. H2SO3 aqueous. Then I've got H+. I haven't got H3O+, but those are the same thing, remember? And then I've got solid sulfur. So there it is. It's almost like I designed it this way and I chose the one that was right above it. That's what I did. So H2SO3 plus 4H plus 4 electrons gives solid sulfur plus 3H2O. So going back to the cell diagram here, you can see that H2O isn't part of it, and you've got this platinum here. We just ignore the platinum, and then we look for the reaction that involves all these other things over here. Does anybody have any questions? Okay. So I know that for the first one, that's the one I have to flip. So I flipped it automatically. I just did it automatically. I didn't even write this down. But as a reduction, it was copper 2 plus 2 electrons gives copper, and it was positive 0.340 volts. All I've done here is just flipped it automatically. Remember, I flipped it because the first one is always the anode. It's where oxidation is occurring. So I always know that I have to flip the first reaction, which is exactly what I did. Now, the other thing I do is I multiplied the top reaction by 2 in order to make the electrons even out, because I want to be sure that I'm transferring the exact same number of electrons from the anode to the cathode. So I've got 4 electrons on top here, 4 electrons on top here. Now remember, when I multiply by 2, it doesn't change the cell voltage. See that? It was negative 0.340. Now it's still negative 0.340. So the copper is turning into copper 2 copper 2 plus 4 electrons, and we don't change the cell voltage. So the E0 cell is going to be the sum of those, which is going to be 0.109 volts. And there's your total overall reaction here. Does anybody have any questions? Right. Once we've done that, then we can calculate the delta G value. We use 4 for the number of electrons transferred. That's why it's going to be important for us to balance these. And the Faraday constant, and then the cell voltage that we calculated. And that comes out to be negative 42.1 kilojoules per mole. Now, back a couple of days ago, I showed you the link between delta G and K. And we can calculate K using this equation here, delta G equals negative RT ln of K. And that allows us to calculate K. All right, I'll show you on Thursday, how all of this applies, obviously, to what you're going to be doing on the test. But here's the summary of what we know about the signs of certain things that we've talked about. If delta G is less than 0, that is, delta G is negative, then we're talking about spontaneous processes. That also means that K being greater than 1 is also going to indicate a spontaneous process as well. And we can get that from this equation up here, negative RT ln of K. If K is greater than 1, then this value will always be a negative value. If E0 cell is greater than 0, then that's going to indicate a spontaneous process as well. So positive E0 cells. Non-spontaneous reactions are always going to have positive delta G noughts, a value of K between 0 and 1, because K can never be negative. And then E0 cell being negative will also be a non-spontaneous process as well. All right, I think that's about as far as I had wanted to get with that today, but I did want to mention one other thing before we go here. Going back to test 3. So test 3, let's look at the syllabus here. Test 3 is going to be 70% for test 3 that you'll be doing. But there's also going to be 20% for some essays that you'll need to do as well. And then there's also a units quiz as well. That's not done under honor lock, but it's a quiz that is going to test your ability to apply units. You'll see what that is. You can have unlimited attempts at that, by the way. So you shouldn't have any real difficulty with that. And that's plus any test 3 extra credit as well. But I wanted to briefly talk about the essay question here. So you'll find that under notes about the essay questions. This is something you'll hand in using a Dropbox. And these are the topics that you're going to talk about. So their essays are 50 words each. Each essay needs to include a reaction that relates to what you wrote in the essay. For redox processes, half reactions and full reactions are expected. These are all actually redox processes. You can find information about all of this in your textbook or on the internet, so anywhere you want. I'm not looking for you to even cite anything here. You need to complete all of these, all 7 of these. And here's an example of what I'm looking for. This is an example of 1 page here. So it shows you the 50 words, the 2 reactions, and the full reaction over here as well. So this is an example of one of the pages that a student's done. You'll notice the student signed across the page as well. Additionally, I'm going to get you to put a fork on the page too. I'm going to include that as something that I'm going to put into the Dropbox. Now, the reason for that is so that people won't copy this from semester to semester. So if you put a fork on there, next semester I'll choose some other object for people to put on there as well. So you'll put a fork on each page. Everybody has access to a fork, I'm sure. And if you don't include the fork, I'm going to make you resubmit it with the fork. All right, does anybody have any questions about the essay questions? I'd recommend getting that done quickly. Don't wait until the day before the test, because that's when it's due. It's due on 11:59 p.m. on the night before the test is due. A lot of people do leave it to the last minute, but it's not really a good idea to do so. All right, does anybody have any other questions? Okay, we'll leave it there for today, and I will see you all on Tuesday. Thanks for coming.
Have a good weekend.
You too.
Thank you.